48 light-years away, a rocky world is leaking something into space. Something scientists once feared it had already lost forever. But an atmosphere does not make this another Earth. Beneath those clouds could lie ice, dark ocean, or an entirely barren surface. Scientists never photographed those clouds directly. Instead, they found a chemical fingerprint hiding inside the faintest sliver of filtered starlight.
But one fingerprint cannot explain an entire world. To decode it, we must revisit nearly a decade of clues and contradictions.
The planet circles a cool red dwarf, a star smaller and dimmer than our sun, but its appearance hides a violent history.
At roughly 48 light-years away, LHS 1140 is cosmically nearby. Its orbit lies inside the habitable zone, where temperatures might permit liquid water, but only if several hidden conditions are exactly right.
The label sounds promising, but it reveals nothing about breathable air, oceans, pressure.
Astronomers first discovered LHS 1140b when its tiny silhouette repeatedly crossed the star, removing just a fraction of its light. That shadow revealed the planet's size, while its gravitational pull made the star wobble, allowing astronomers to estimate its hidden mass. The result was a world approximately 1.7 times Earth's radius, large enough to enter the mysterious super-Earth category.
Yet it contains roughly 5.6 Earth masses, producing stronger gravity and raising a crucial question about what lies inside.
Its density is too low for a simple enlarged Earth, suggesting that this planet contains something lighter beneath its concealed exterior.
For years, two possibilities survived: a small planet wrapped in hydrogen, or a massive world containing an extraordinary amount of water.
Then Webb challenged the first possibility, finding evidence against a thick hydrogen-rich envelope, and making the alternative far more intriguing. Models now suggest water could form roughly 9 to 19% of the planet's mass, an astonishing quantity by terrestrial standards.
Under some climate models, a circular liquid water region could face the star, surrounded by an immense landscape of permanent ice.
But no telescope has photographed that ocean, its clouds, or any surface feature. Before discussing oceans or life, astronomers faced a more fundamental mystery. After billions of years, had any atmosphere survived at all? High-energy radiation can heat the upper atmosphere until individual atoms accelerate beyond gravity. Young red dwarfs can remain violently active, bombarding nearby planets with radiation during the most vulnerable stages of atmospheric formation. Other nearby rocky worlds have produced few convincing atmospheric detections, creating a warning: survival around red dwarfs may be exceptionally difficult.
LHS 1140b possesses one defense: its power gravity, which can pull escape heart.
Its star appears quieter today than many red dwarfs, yet the planet still carries the invisible scars of its star's violent youth. Across billions of years, any light primordial atmosphere should have changed dramatically, making the next prediction seem almost impossible to confirm.
Researchers predicted that hydrogen escaped most efficiently, leaving a helium-rich upper atmosphere hovering above heavier, still hidden gases far below.
Those heavier compounds might include important volatiles, but an opaque atmospheric barrier prevents present telescopes from identifying their deeper composition.
Helium offered a way through. It leaves a distinctive near-infrared fingerprint that powerful ground-based spectrographs can detect during planetary transits. During transit, only a tiny fraction of starlight filters through the planet's edge, yet that contaminated light carries its atmospheric chemistry.
As the planet moves, its chemical fingerprint shifts in wavelength, separating genuine planetary gas.
To capture that movement, astronomers turn toward the Magellan Clay Telescope, standing beneath the exceptionally...
Its wine-red spectrograph divided near-infrared starlight with extreme precision, searching for a helium signal buried beneath layers of instrumental noise. Then geometry offered a rare opportunity. Both known planets crossed the same star during one night, creating an almost perfect comparison.
The smaller inner planet, LHS 1140c, receives stronger radiation.
But Planet C produced no corresponding helium signature, an unexpected silence that made the approaching outer planet far more important. When LHS 1140b finally crossed the same star, the spectrum changed, and a faint feature began moving through the data. The suspected helium signature moved with the planet instead of remaining fixed to Earth or the star, surviving the first critical test.
Its velocity matched LHS 1140b precisely, powerful evidence that the escaping gas originated around the distant planet itself.
The 2024 observation revealed helium absorption with an extended upper atmosphere.
1 year later, researchers returned with the same telescope and watched another transit, expecting the helium fingerprint to appear again.
It did not. The 2025 observation found no comparable absorption, transforming an apparent confirmation into a deeper atmospheric mystery.
That disappearance does not automatically erase the discovery. Atmospheric escape can strengthen or weaken as stellar conditions change between observations.
The upper atmosphere may expand beneath stronger radiation and contract when the star quiets, producing something like planetary-scale breathing. Continued replenishment would imply a substantial hidden reservoir below, not merely a thin leftover cloud clinging weakly to a bare surface. Yet another possibility remains. Occasional geological releases from a mostly barren planet could briefly imitate evidence for a permanent atmosphere. The more exciting alternative is a long-lived atmosphere that continually loses gas while remaining globally stable beneath the escaping helium.
Planet C's silence strengthens the case that Planet B's signal was not simple contamination, but it also deepens the comparison mystery.
And helium is not breathable air. This detection provides no evidence for oxygen, Earth-like, or the measurement reaches only the escaping upper atmosphere, leaving the lower pressure, weather, clouds, and surface chemistry almost completely unknown. Researchers interpret that upper layer as helium-rich and hydrogen-poor, the expected aftermath of atmospheric escape operating across immense spans of time. Heavier volatile molecules may remain trapped beneath it, but scientists have not yet securely identified what those hidden gases actually are. A retained atmosphere makes the proposed water world interpretation more compelling, yet it still cannot prove that a liquid ocean exists. Because LHS 1140b receives less energy than Earth, much of its possible water may remain locked beneath permanent ice. Near the point facing the star, however, atmospheric heat transport might sustain a localized liquid region beneath an unmoving crimson sun. Whether water remains liquid depends on atmospheric pressure and composition, two decisive quantities that scientists have not yet successfully measured. A thick atmosphere could carry warmth toward the permanent night side, preventing its gases from freezing and collapsing onto the surface. But nothing in these observations reveals life, vegetation, technology, oxygen, a methane biosignature, or any form of biological activity.
The habitable zone describes the energy reaching an orbit.
Even without life, atmospheric survival on a temperate, rocky world would mark a major step in understanding planets beyond our system. And if helium reveals one atmosphere, the same technique could expose hidden atmospheres surrounding other nearby rocky worlds orbiting red dwarfs. LHS 1140b has therefore joined the Webb and Hubble Rocky Worlds program, where multiple observatories will investigate it together. Future Webb observations will search for water signatures and test whether a stable lower atmosphere truly exists beneath the escaping helium.
Carbon dioxide would constrain climate and pressure, revealing whether temperatures could support liquid water or instead produce an entirely hostile environment.
But the answer may require 4 or 5 years of repeated observations, because one transit cannot securely reveal an atmosphere this distant. Clouds or high-altitude haze could hide crucial molecules, allowing a substantial atmosphere to exist while remaining frustratingly difficult to characterize. Even the star can imitate planetary chemistry. Changing star spots contaminate transit spectra and create signals that resemble atmospheric absorption.
Simultaneous measurements could reveal whether helium variability follows the star, the planet, or changing conditions inside the instruments themselves.
If helium returns during another transit, the case for a persistent atmosphere with variable escape will become considerably stronger.
But if it remains absent, researchers must reconsider how the original signature appeared, and whether an entirely different process created it.
Finding water vapor would support a stable volatile atmosphere, but it still would not prove surface oceans, habitability, or life.
Carbon dioxide could warm the planet, yet different concentrations might create anything from frozen wilderness to an oppressive, uninhabitable climate. Because detecting an atmosphere is only the doorway. Beyond it wait harder questions about pressure. Earth, Venus, and Mars all possess atmospheres, yet their surfaces followed radically different paths, warning us against easy conclusions about distant worlds. Life as we understand it needs stable chemistry, usable energy, liquid solvent, and time, far more than one escaping atmospheric clue. And with present technology, no spacecraft can reach this world. Its red star would remain distant for thousands of human lifetimes.
So light becomes the messenger, crossing 48 years of darkness before delivering a fragile chemical fingerprint into a telescope on Earth.
Helium is only the first illuminated fragment of a spectrum whose pressure, clouds, climate, and deeper composition remain hidden. The discovery transforms LHS 1140b from a measured sphere into a dynamic world actively evolving beneath radiation from its star. Every escaping helium atom carries evidence of that evolution, preserving clues about formation even as the evidence disappears permanently into space.
But the most important question remains beneath the clouds. Does the surface contain ice?
For now, the honest conclusion is powerful but limited. Helium appears to be escaping from an atmosphere surrounding LHS 1140b. During the next transit, telescopes will turn toward the system again, searching for gases, pressure, and climate hidden beneath that helium.
A future spectrum could reveal water, carbon dioxide, or neither, separating a frozen world.
We may finally have detected its atmosphere, but we still cannot see the world that atmosphere protects, or what waits below. So what should astronomers seek next? Water, carbon dioxide, or evidence that this fragile atmosphere can survive for billions of years?